Continuing, happy to introduce Christof, obviously my collaborator, but he's going to talk to us about U1 lattice 2D, the U1 lattice field theories at non-zero topological angle. So take it away, Christof.
Thank you very much. Thank you very much to you and the other organizers for having me here. And yeah, as Tim said, I will be talking about 2D U1 lattice field theories at non-zero topological charge. This is work done together with Tim, obviously, and two students, Daniel Göschel and Dominik Hirtler. But I should point out that this is part of a larger program, which is mainly initiated by Tim, where also Nabil has contributed and other students, where we try to analyze 1 billion lattice game theories, the role of dualities, topological terms, and this is only a subset of this program, which I will be talking about today. So, 2D U1 lattice field theories at non-zero topological charge. And if you want to study such theories on the lattice, you face several challenges. There are three main challenges you can identify. So I wrote down the generic form of a partition sum integral over the gauge configurations. This is some generic meta fields. You have the standard part of the action, and then you have the topological charge. Whenever you put a theory on the lattice, you have to discretize your action, but also your topological charge. And here is the first challenge. You can do something which is called a naive discretization of FF dual, or in our case, F mu nu epsilon mu nu. But then you will not get an integer valued Q. And so some of the symmetries appear only in a continuum limit. So you go to large lattices, finer lattices, and then somehow on the way you start to recover the symmetries. And if you want to understand phase transitions, which are related to breaking of these symmetries, this is clearly a challenge if you do not have it implemented properly. So this is something which we will solve by using a Villain discretization in higher dimensions, also with some additional constraints. So I would like to refer to that as generalized Villain discretization. This completely solves this problem in a very elegant way, but only for 1 billion theories so far. The second obvious challenge is the complex action problem. So if we want to study a theory on the lattice, we want to interpret the Boltzmann factor as a kind of probability, and even the boldest mathematicians so far have shied away of defining complex valued probabilities. So this you also have to overcome this problem. This problem appears in many guises, not only when there's topological terms, but also when there's finite density. And over the last years, we have been developing so-called world line and also world sheet representations, which allow to solve some of the complex action problems simply by mapping to different degrees of freedom. It's an exact mapping, and I will try to explain a little bit how such a mapping comes about. And then the third challenge, if you deal with fermionic matter, then even after you have solved the discretization problem and the complex action problem by going to such a world line representation, if you have fermions, the world line still can have signs, and also a negative probability is not something which is useful in a numerical simulation. It doesn't exist. And here, I don't really know how to say it, but it's a kind of miracle that two-dimensional massless staggered fermions, they are, for some weird coincidence, all the minor signs which you have in your fermion world lines disappear. I will try to discuss this also a little bit as we go. Good. So let's start simply with our first working example, which is U1 gauge fixed theory, which is a topological term in 2 dimensions. And I write down, just to have a starting point, the familiar continuum action, so with derivative terms that couple to the gauge field, mass term, cortex-self interaction, gauge field action, and our topological term. What is standard in our approach is when we go to the lattice, I told you we have to take care of the gauge fields in a special way, but for the meta fields, we can use a standard discretization of the lattice. So the integral over space-time is replaced by a sum over a square two-dimensional lattice with periodic boundary conditions. Obviously, this is the mass term, this is the quartic term. The derivative terms are implemented in the simplest way by nearest neighbor derivatives, made gauge invariant by link variables, which are gauge transporters along one link of the lattice, and the exponent we will later identify as our gauge degrees of freedom. However, usually in a lattice approach, everything, also the gauge action, is formulated in terms of the link variables. And just to remind you, I guess most of you have seen this before. You place the link variables along the links of an elementary square on the lattice, a so-called plaquette. You take this product. If you sum a plaquette plus its complex conjugate, then if you expand in small field A, you will get the f mu term. It's also a simple exercise to see that this will give rise to the epsilon mu f mu term, which we need for the topological charge.
So for the matter action, why do you have it +4 then?
Sorry. So here, this you can write in essentially as a covariant Laplace operator. And for a Laplace operator for the discretization, you always have a 3-point formula. So one step forward, one step backward, and a term which is on-side squared, which has exactly the same shape as a mass term. And this is why you get this extra factor of 4. Simple discretization. Sorry, I forgot to mention it. Okay, but here you see, obviously, so this is the imaginary part of this complex phase here. This is not necessarily an integer. And in a very naive paper some 8 years ago by now, we started with this discretization because we had not understood these ideas which came out of the work with or initiated by Tin. And there you can have a look how hard it is to try to learn something from a lattice simulation when one of the symmetries, or in particular the symmetry you try to study, because it becomes broken in this theory if it's not properly implemented. It's very hard and not very conclusive.
Sorry, you have in mind the charge conjugation.
Charge conjugation.
At theta equal pi.
At theta equal pi, yeah. Thank you for, I'm always miraculously speaking of symmetry. Yes, this theory obviously has a charge conjugation symmetry, which I will discuss in detail. So phi goes to phi complex conjugate, and A goes to minus A. You can see this is a symmetry which, however, reverts the sign of the topological term. This is linear in A, so if you go from A to minus A, it obviously changes sign. But if you raise this to the exponent with e to the I theta, you see you have two symmetry points. The trivial one, theta equals 0, so no topological term, or theta equal pi is the second solution. And this is exactly the symmetry which we are going to study. I will discuss this in more detail, but since I mentioned it twice, thank you for reminding me to be more explicit here. All right, so what is the alternative to a naive discretization of the lattice? So we want to keep, I mentioned this already, we want to keep the discretization of the meta field as we have learned it in lattice school and use our link variables. So the link variables are parameterized with the e to the I some a x mu. And then you can naively identify the field strength with the exterior lattice derivative. So you take this signs with signs according to the orientation, combination of the exponents along the four links on your plaquette. This gives you the exterior derivative. It's a discretization of f12 if you want. And this would be a first attempt. People have even played with this. It's called non-compact discretization on the lattice. But you miss something very important, namely the gauge links are invariant under shifts. It's clear that you can always get 2 pi times some integer, you will get the same link variable, but the exterior derivative will pick up an extra term. And if you do it with a Wilson action, then you have a cosine essentially of this object here, then this is eaten up by the cosine. But you can also promote this to a symmetry which you can gauge. So what you can do is you generalize your field strength to be the exterior derivative plus something which is a plaquette-based gauge field, which you sum over and which eats up the terms which you generate by this shift symmetry of the link variables. This is the idea. This is an idea that is not entirely new. It was formulated many years ago, and it goes under the name of Wheeler action. But to our knowledge, it has not been applied to study theories with a topological term, and in higher dimensions, we have very interesting generalizations one can study with these additional constraints which I mentioned. So, this is the idea. So let's look at what we have achieved. So we have created this generalized Villain-Boltzmann factor, which also includes a topological term. I have to step a little bit forward that I can read what I'm pointing at. So here you see our definition of the, sorry, there's a mistake, there should be the dA here, not the F. I changed my notation halfway. But here you see it. So this is what we just identified as our field strength tensor. So it's the exterior derivative plus this additional new auxiliary variable, Wheeler variable, which you sum over all integers to eat up the terms which you create by this shift symmetry. The topological term was the integral of f12, so we don't have a square here, this is just linear. And this is the Boltzmann factor, which now also in the definition contains this summation at every plaquette, and I'm dropping this 1, 2 indices. The plaquette is labeled by the lower left corner, which I call x. So at every plaquette, you have such a Wheeler variable which you sum over all integers. And then something nice emerges, because it's clear that if we work on a torus, or in our case a lattice with periodic boundary conditions, if you sum the exterior derivative over all of this torus, of course this contribution vanishes, and then all what remains for the topological term is the sum of these integer valued Wheeler variables. This is a very natural, geometrically beautiful definition of the topological charge. So, topological charge is simply identified as the sum over the values of all the Wheeler variables. It's clearly an integer, so we have implemented this symmetry exactly. And in our action, the charge conjugation now acts as flipping the sign of the gauge fields. You have to complex conjugate the meta fields. I didn't display this here. And at the same time also change the sign of these Wheeler variables. It's a combined transformation which you have to implement. And you will see this transformation in a third disguise, namely when I switch to this word line interpretation, where it also has a nice, beautiful geometrical picture.
Question?
Yes?
In this formulation, when you simulate, is there any issue with having to sum over infinitely, over running from minus infinity to infinity, or?
So first you see that it's strongly suppressed. So even if we had this problem, this wouldn't be an issue. So people have been simulating this, not going to these world line simulations, and even if you do a local Monte Carlo change, okay, you sum this exponential from n equal minus 10 to plus 10, what you cut off is so small it doesn't play a role. So this is really not an issue.
What about for a? Do you integrate from 0 to 2 pi? Do you sample from 0 to 2 pi? Or
you will see I will get rid of the a, because we have a beautiful formulation, but we still have the complex action problem. So I'm only halfway there at the theory which I'm going to simulate.
Maybe I can also comment. I mean, you can the discrete gauge symmetry you can use to gauge fix A's to be in the interval 0 to 2 pi, and that will solve the issue. But he's going to go in a dual representation where this is just some numerical factor.
Okay, so the next step is to overcome this complex phase. So you said theta equal to pi is just plus and minus signs, but again, we don't know about negative probabilities. And this proceeds in two steps, and I'm going to make both of them plausible without working out all the details, because partly this is a little bit clumsy to write down. Again, here we have our metal field partition sum. Discretization you have seen before, and it is clear that this is a gauge invariant function of these link variables u, x, mu. And then we know very well what are possible gauge invariant terms we can construct on the lattice. This is simply chains of link variables on a closed loop. So we can have arbitrary loops on our lattice. For every link that is visited by the loop, we place, or we take as a factor the corresponding link variable, and as soon as it is a closed loop, this is a gauge invariant quantity, and there are no others. So the partition sum, which I have written down here, is a sum over generalized Wilson loops that are dressed with these link variables, and they come with weights. So these loops are generated from an expansion of these hopping terms here. So you leave this in the exponent, so it's not a perturbative expansion, it's really a hopping expansion. You expand this, and the expansion coefficients somehow turn into your new variables. And it's clear from general reasons, hang on a second, that it has to be closed loops, and then it's just a question of calculating the weights. Sorry.
Sorry. You have 5 to the 4th. How do you carry out the integration? So I agree that it's gauge. It's gauge invariant. So you don't know exactly what W is.
What do you mean W?
No,
I know exactly what it is. It is written down in the form of an integral over the modulus of the fields. If you want to, I can show it.
Okay, so you have a formal way of...
Exactly, and you don't need this integral itself, but you need its moment. So you have you integrate over the modulus, and there's in the exponent the weight of r squared and r to the power 4 if r is the modulus, and then downstairs you have inserted powers of r to the power n. But in a numerical simulation, the terms that appear, you get away with the first 20, 30, at most 100 moments. And you can calculate them to arbitrary precision with Mathematica. You pre-store them on your computer, and for your stochastic process, whenever you need them to make your Monte Carlo decision, you call them up. So this is how we proceed. Okay, you don't have to calculate in closed form, it's not necessary.
How easy it is to calculate these W's?
Medium much work. So if we had another 15 minutes, I could walk you through the arguments. It's relatively easy.
Because I remember that the hopping expansion has a finite radius of conversion. Do you have to?
Not in this case. Not in this case. I mean, there's many hopping expansions, fermions, and so on.
Okay.
But here, this is perfectly conversion. You can apply higher mathematics theorems. A student of mine did that. And you can write it in terms of these integrals, which you cannot solve in closed form, but you only need them numerically, and you can have precision as high as you want.
The phi is not unimodular, right? Because of
No.
Okay.
You can also replace this, of course, by unimodular phi. It's a slightly different theory, but I guess the physics it describes is very similar. Anyway, we started with this one, and we stay with that one. Good. So. Then you just need to come up with an efficient way to describe these flux variables, and this world line that we describe them with flux variables, and you see them at work here. So every link of the lattice we place an integer, and if this integer points in positive direction, then this here is +1, this points in negative direction is -1, but it can also be +3, or this is -2, no, +2, -2, and so on. This is how we describe them, but they have to be closed contours, and since you asked how do I calculate it, this all comes out of the expansion. They have to obey a zero divergence condition, and this is in the final form here implemented as a constraint. So this is a Kronecker delta, and the object that has to vanish is the divergence, and we all learn that if divergence vanishes, then flux through something is net zero, and you can just draw a picture. So the number of units of flux that go into a site X is the amount that comes out, and you see my little sketch, if I didn't make a mistake, at every side of the lattice there's the same number of arrows going in as going out. This is a constraint. So you trade your original unconstrained variables for something that is constrained and potentially harder to update, but as you will see in a minute, it solves the complex action problem. Good, and then you have this configuration of all admissible arrangements of these flux variables ensured by this constraint. Here are these pre-tabled integrals, and you see they only depend on this integer in a certain way, and you can calculate these moments that you need. And then at every link of the lattice you have activated the corresponding link variable. So if this j is equal 0, then we are maybe here. There is no piece of Wilson loop going through, but wherever you see non-vanishing arrows, this means that this j is a non-zero integer. Positive if you run forward, negative, which means complex conjugation for the link variable, if you run through it negative. Okay, this all comes out of one calculation, which I tried to avoid, but give you a little bit the logic. Good. So now we have achieved the following. Now let me go back once more. We have organized the meta degrees of freedom such that the coupling to the gauge fields is downstairs from the exponent in the form of these phases. So here we are hopeful that we can integrate this out in the end. And the action which we have written down is quadratic in this A, so it's a good chance that we can solve this Gaussian integral, which is true in the end. So we now have to look at the full partition sum. So here we have our loop representation. Here we have the Boltzmann factor, which we have discussed before. And now we have to integrate out the gauge fields, which brings me back to your question, Max. We get rid of them, we don't update them at all. Okay, we'll see how this works. Before we can calculate this Gaussian integral, it's convenient to do a Poisson resummation. So this is the standard equation where these Villain variables are traded by plaquette occupation numbers, I call them, which are again integers. You see them here already. So when, for example, these are plaquette occupation numbers depending whether they're mathematically positive or negative with values +1 or 0 ones. Plaquettes that are empty have obviously plaquette occupation 0. So this is the interpretation, but it's simple mathematics. And also that brings the dependence on the gauge field into this exponential form. So we have the exponential form from the Wilson loops here. We have the occupation numbers of these plaquettes coupling to something that is linear in this gauge fields A. So we can integrate them out. These are all integers. So this integral will simply, here you see the final form. So I've taken this, I've inserted this, I reorganized terms. So we have a sum over our flux variables, our plaquette occupation variables, sum over Villain variables has disappeared, was replaced by that. We still have our flux conservation constraints, we still have our weights. We have the new weight factors for the plaquette. So every plaquette costs Boltzmann factor if you occupy it. If you have higher occupation, it becomes even more expensive. And then there's a remaining integral, which you can reshuffle a little bit here. And then you see if I integrate this out, I get yet another Kronecker delta. So in addition to the constraint which we had here, you get a second one, which we'll discuss in a second constraint that ties the plaquette occupation numbers to the metafluxes. And we have the weight factor from before and the new weight factor. And you see, even for finite theta, this is completely harmless, it's real, it's positive. You can do a Monte Carlo simulation, but your life got a little bit more complicated because you have to obey the constraints. So let us look at the constraints. This works also in arbitrary dimensions, so since I was too lazy to draw a new picture, I took a three-dimensional one. Here we see again our flux lines. We see the plaquette occupation numbers. We already discussed flux conservation, which means that every side of the lattice you have to have the same number of red arrows going in and going out. And the second constraint, which is due to the gauge symmetry of the theory, tells you the following. Whenever on a link of the lattice I have flux, it has to be compensated by another flux. So for example, you can have two metafluxes running in opposite direction, they will cancel. But you can also have fluxes from occupied plaquettes, which can be compensated either by a neighboring plaquette, where the flux runs in the opposite direction along that link, or by metaflux. So your degrees of freedom are either closed surfaces of gauge flux or open surfaces bounded by metaflux. Of course, these are representations which are known for many theories, but it's nice to work out this example for QED in this case, so scalar QED in this case. And the idea is simply to simulate in this language, you got rid of all complex action problems. And it also works, this is interesting, maybe a little bit of a side remark. So you can also look at, say, the relativistic Bose gas at finite density. Then you introduce an asymmetry between temporally forward running and backward running loops. And the net particle number becomes the total winding number of these flux lines around compactified time, which I find a very appealing picture, because in a standard quantum field theory, for the particle number you have to write down something complicated. In this language it simply becomes a topological invariant, and you can couple the chemical potential simply to this winding number, and this solves yet another quite hard complex action problem in lattice simulation. So we've been playing with these world sheet representations for quite some years, but mainly motivated by finite density, until Tin suggested to also look at other programs. Good. So, what are we doing? First example, we started, you've seen it before, 2D U1 gauge Higgs model with a topological term. Here again, the continuum action, charge conjugation I've mentioned before. Phi goes to phi star, A goes to minus A. We have exactly transformed this corresponding lattice theory into this worldline worldsheet form. And now you can ask the question, how does charge conjugation work in this representation? And this is also quite intuitive. Namely, essentially, you have to revert the orientation of the loop. So the orientation of the loops knows about the charge. And you have to flip the plaquette occupation numbers. But then it's interesting, if you look at charge conjugation at theta equals 0, you just flip, while at theta equal pi, there's an additional shift. There's a small difference in the implementation, of course, whether you do it at theta equals 0 or theta equal pi. We are interested in this case, so we study this system at theta equal pi and explore if charge conjugation symmetry can become broken. Parameters here, we kept a fixed value of the quartic coupling. We studied two different values of beta. If you increase beta, your lattice becomes finer you go closer to the continuum limit. And we vary essentially the mass parameter, trying to drive the system into a Higgs phase and see what happens. Order parameter is the first derivative with respect to theta. Here you see it. You pull from the exponent essentially the sum of the plaquette occupation numbers. This is odd under your symmetry, so it's a suitable order parameter. Here you see the results. So we studied the expectation value of the order parameter. We studied the corresponding susceptibility as a function of the mass squared, or of this combined parameter you asked about. So this is the m squared plus 4. Okay, whenever you go below 4, your mass squared becomes negative. And this is why we put the second scale also up there. You can apply all these nice techniques which Anders talked about, various finite size scaling plots techniques, collapsing the data, and we managed to calculate the critical exponents, and this is a C2 symmetry of the system, and you expect that this to be Ising, and we get there within 1% or so of accuracy. So we were quite happy that this came out so nicely. I think I'm close to running out of time, but I wanted to discuss a little bit the flavor of what comes into the game when you start adding fermions. The program is the same, but I mentioned there's a third challenge, namely that fermions, when you introduce them, they create additional minus sign simply from Pauli statistic. So, what are we studying here? We studied the massless Schwinger model with a quartic self-interaction and a topological term. So you'll see in the second half of the action, the first half is this scalar squared quartic self-interaction, and then the Dirac kernel acting on inside the bilinear psi-psi. Discretization of the gauge fields as before, using our Villain construction. Here you see it again. And of course we still have to integrate over the fermions, and I am using here the so-called staggered formulation, which means we are using one component Grassmann variables, and instead of gamma matrices, which you see here, the Dirac degrees of freedom are distributed over a hypercube, or here in 2 dimensions over a square with an exact transformation. This is space-dependent rotation in Dirac space, staggered transformation. And this staggered transformation diagonalizes the massless Dirac operator, so your 4, or in 2 dimensions 2 components become degenerate, and you throw away one of them, or in 3 dimensions 4 of them, to reduce the so-called doubling problem. This is the construction which is underneath here. So you see again the discretization of the derivative term here. The gamma algebra was converted into this staggered sign factor. So it's just depending on which direction you go, it's either constant or something like a checkerboard pattern. And for the discretization of the quartic term, it's obvious that if these are one component Grassmanns, I cannot simply square them as I did here with this 2 component representation, but we average over nearest neighbors, and in the continuum limit this term will reproduce exactly this form here. And since we smear it over 2 directions, there's the extra factor 2 here. Good. So again, we need to solve the complex action problem from the topological term, which means we have to go to world lines and world shades. But now comes the problem. So we can come up with a world line representation for the same reasons as before. Gauge invariants, these have to be loops on the lattice dressed with gauge links. This fermionic case to calculate the representation of terms of loops. You just have to separate this Gassman integral, and what you get is loops, but each loop can only carry a maximum of flux 1. This is due to the fermionic nature, so you cannot have flux 2 on these world lines. So you can have flux +1 and of course -1 for going in the other direction. And this allows also for what is known as dimers, of course, namely a super short loop where it goes forward and backward. But in this loop, obviously, the complex phase from the gauge link disappears, so they do not couple to the gauge field. So you have a sum over all these loops. And these loops come with signs, so you can work out the sign. There's always a minus, and over a minus sign, then half of the hops go in negative direction, so half of the loop length brings a minus sign. And then from these staggered signs, you can show that around the plaquette is always -1. So what you can do is you take this loop and you span a surface by this loop, and you count how many plaquettes you need, and this gives you this area of the loop. This also contributes to the sign. This is from the staggered sign factor. I'm almost done. And the interesting thing is that for 2D massless staggered fermions, you can show that all admissible loop configurations, so every site has to be visited either by the endpoint of a dimer or be run through by a loop. You can show, it's a small constructive proof, that no minus sign remains. It's a miracle, or maybe you have a deeper insight from me. This is an interesting observation, which maybe has a deeper meaning I don't understand. Anyway, in this case, the problem is solved. It does not work when you have mass terms. It does not work in higher dimensions. You can easily construct counterexamples. So, we are ready to simulate. Here you see the theory again. Here we have the constraints we have seen before. We have the weight factor for these dimers. Here's our coordinate coupling. Here's the weight factor for the gauge fields. Fluxes for fermions, only -1, 0, or 1 is allowed, and we have to activate the dimer to fill the remaining sites. Typical configuration looks like that. Again, you see the gauge constraint that works, so at every link, flux has to be compensated by field plaquettes. Here we cannot have two meta lines compensate because fermions don't allow for that. So these are typical configurations. And it's a quite challenging problem to update also this dimer dynamics because it gets very stiff when you have to use warm algorithms and other nice techniques developed in recent years. So here I'm not showing you the original data, but already the rescaled data using some of the formulas which Anders showed us. So you see nice finite volume scaling, different volumes. If you plot them properly with the correct exponents, which are again the 2D using critical exponents which we inserted, you see a beautiful collapse of the data. And now I really have to stop and just summarize. So these simulations of 2D U1 theories with topological terms face 3 challenges. Suitable data definition of the topological charge, complex action problem for the theta term, sign problem for fermions, and of course this also holds for higher dimensions. Euler formulation gives a good, elegant definition of the topological charge. World line worldsheet representation solves the complex action problem, and for the massless staggered case, you even get rid of the fermion signs. We performed Monte Carlo simulations. In both cases, we found that theta equal pi, spontaneous breaking of charge conjugation symmetry as function of the couplings. In both cases, we could demonstrate it's in the Ising universality class. Thank you.
One very quick, urgent question, if there exists.
So I missed that in the scalar case, when you took the scalar to be heavy, you got CP breaking. What was for the fermion? I missed that. What
Same.
Oh, it's the same.
So here, the parameter which we drive is the coordinate coupling. Oh, sorry. Here it is. So if you go to large quartic coupling, the picture is very simple. Then if you go to large quartic coupling, everything is filled with dimers. And then all the plaquette values have to be the same. And then you get a non-vanishing expectation value of Q, which is just the sum of the plaquette incubation numbers. If you have little dimers, then nobody tells you which orientation these have. So you have pluses and minuses randomly distributed. Over space, they average out, and Q goes to 0. So this is in this language.
Why did you have a quartic and not a mass, for example?
You're not waiting for my answer. Go ahead.
It's part of the same question.
There's different answers. So the technical answer is that you can't do the simulation because you have the sign problem back. Another answer is you could absorb the theta dependence.
Okay.
Do we have more answers, Tim?
No, you
No,
cannot.
well, you cannot absorb. It's non-chiral. So you
Yeah,
get
yeah.
m to the I theta. You get a complex mass.
Yes.
So
Yeah.
it's a sign problem again.
It's a sign problem. This is true.
Anton, very
No, we confused about this discussion of fermionic model, which was very brief.
Yeah.
So these are massless fermions.
These are massless fermions, but
interacting. So
but they're interacting, so there might be a mass term generated.
it will be generated.
Yeah,
because
that's
it's
a
breaking
fine
chiral
tune,
symmetry.
yes.
Well, it's preserving. It's
So
preserving.
there's no chiral symmetry.
No.
No, there is chiral
There's a
symmetry.
Z2 chiral symmetry.
No, I'm talking about, I just want, usually in continuum, you can rotate, for massless fermions, just rotate the theta angle because we have, the axial symmetry allows you to rotate it away. So here we don't have chiral symmetry. Otherwise, theta
So the chiral
There's no full chiral symmetry because it's the mass term squared basically that he has. Show the.
sorry, I was going in the wrong directions. Not yet. Not yet.
Here.
There we go.
That's the.
okay, so not chiral symmetry.
No.
So there's no full chiral, but there's some Z2 chiral symmetry.
Yeah. Exactly.
It's a long
Not just fermion. Well, it's Z4, I guess,
Yeah.
including fermions. Okay, let's thank Christof. Not for going over time, but giving a nice talk.